Fermi theory of beta decay. Here Fermi explained wonderfully the shape of beta spectrum. Here we are going to discuss about how this Fermi arrived or explained the beta spectrum. So this shape will give you the beta spectrum shape will give how much energy is taken away by the neutrino, or what are the different probabilities or different proportion of energy divided between beta particle and neutrino. Using quantum mechanical approach, this problem can be solved wonderfully. Okay, it can almost explain. This theory can almost explain this graph or its shape. So, and we know that this theory is known as the Fermi theory. Okay, when we discuss about the alpha decay, there comes the tunneling problem, nuclear interactions, etc. But when we deal with the beta spectrum, there won't be any tunneling effect or anything like that, or Coulomb barrier, or penetration or something. There is no. There will be okay. In the case of beta spectrum, there will not be that type of interactions, because we know that the beta particles or neutrino both are leptons. They will not involve in any nuclear process, because they are leptons. They will undergo the weak, they will act only by the weak forces. We already discussed all these things. Okay, so the weak forces are involved in this process. In the case of beta spectrum, the force involved is the weak force. So we can use the time dependent perturbation theory of quantum mechanics here. The main result of the time dependent perturbation theory is that if you have a system and we have an initial wave function psi I and a final wave function psi f, and there is a transition from the initial state to final state, and the probability of transition is given by, or the rate of transition is given by lambda is equal to 2 pi by h cut vf square rho ef. So the metric element vfi is the integral, which is given by vfi is equal to integral psi f star v psi I dv. This psi f star will give you the final state of the final state, and psi I is the initial state. We know that this psi f state contains the three particles, that is daughter nucleus, wave function of daughter nucleus, and wave function of that proton and or electron, or wave function of neutron or antineutrino. Sometimes it may have the wave function of electron, antineutrino, and the daughter nucleus, but the psi I is the initial wave function of the particle nucleus that involve only the initial nuclei, and here there contains three terms. Okay, so this is given. This is known as the Fermi golden rule, and we use this Fermi golden rule to calculate the energy of beta particle. Okay, so this rho EF indicate the final energy state. So rho EF can otherwise written as dN by dEf, where dN is the density of state in the energy interval dEf. So dN is the final state in the energy interval. So psi F. Rho F is the density function, or the number of particles having energy between E and E plus dV. So this transition can be written as psi I initial state to final state, and this wave function is given by this, and transition probability is actually. So actually what happened in this reaction is, we know that a neutron is converted into an electron, a proton, and an antineutrino, and we will study that or we will discuss that the neutrons internal structure. The neutron containing two quarks, we already discussed that the bad neutrons and for neutron and protons are baryons. Baryons have three quarks. They are made up of three quarks, and in the case of neutron it's a du, and in the case of proton UUD. So when a neutron is converted into proton, one U and D here, one U and D. So ultimately the reaction may be this D quark is changes into U quark plus a interacting particle, that is matter particle. Oh sorry, this is known as the field particle, W minus boson. So W minus boson is give rise to E minus into U. And charge is also conserved. We know that the charge of the down quark is minus 1 by 3 and the charge of the up quark is plus 2 by 3. So when you find out the charge conservation, it is also valid here. So ultimate, so this process is a quark conversion from a down quark state to an up quark state. So this matrix term involved the properties of the nucleus. So the main dependence of the energy spectrum is came from this expression rho EF, or from dN by dF. Actually, this dN by dF is the important term which will play, or which will decide the shape of this beta ray spectrum. A given transition is more likely to occur if there is a large number of accessible final states. So the final state wave function must include not only the nucleus but also the electrons and neutrino. So this Vf phi is equal to G into integral psi f star. This indicate the nuclear wave function, and phi E star the wave function of the electron, and phi nu star the wave function of this neutrino, and OX, it is the Hamiltonian of interaction into psi I dV. This bracket will give you the wave function of the final states containing final nucleus, electron and positron. And the main part factor which determine the shape of beta spectrum is the density of state. So we know that the number of final state accessible to decay. Okay, so in order to derive an expression for the density of state, we need to know about the number of final state accessible to the decay product. Okay, let us suppose that P is the momentum of the electron and Q is the momentum of the neutrino. Okay, at this point the shape of the energy spectrum can be obtained. We know that obtained from the shape factor. So in order to get the number of state between momentum P and P plus dP, we have to consider a momentum space with coordinate Px, Py and Pz. So if we consider a coordinate system having axes Px, Py, Pz, and we represent this state of the function, or the number of state having energy between E and E plus dV is given by the number of state having momentum P and P plus dP. That's we will get from the this momentum space. So when we draw, we can get momentum P as square root of Px square plus Py square plus Pz square. So the particle having momentum between P and P plus dV, dV is given by, and the volume, its volume is given by 4 pi P square dP. So this is a momentum space. Here instead of p, here we are writing the kx, ky, z, kz, or we can write px, py, pz, etc. So this is a momentum space. The volume in the momentum space for momentum between p and p plus dv is given by 4 pi p square dp. So suppose we are drawing a sphere having we have, in order to get the volume, we can draw a sphere having radius p. So its volume will be 4 pi p square. And dp. So this is a spherical shell. There is a sphere having momentum p and area 4 pi p square. And let us consider the number of in order to find out the number of particles between the momentum p and p plus dv, we have to find out the volume between p and p plus dv, dp and p plus dp in momentum space. So that volume is given by 4 pi p square dp. But we know that this coordinate are px, py, pz, and this it is defined by nx, ny, and nz. So the px, py, pz are defined by nx, ny, and nz. So these nx, ny, and nz are positive quantities. So when we have to take only part of it, because when we go from this axis to this for ky, when we go away from here, ky will be negative. When ky is negative, this ny will be negative. That is not possible. So we cannot go in negative ky direction, and also we cannot go for negative kz direction because at that point nz will be negative. That is not possible. We cannot go for the negative kz direction also. At that point also the nz will be negative. So when we consider the positive nx, ny, and z, we will take 1 by 8 of this volume. So volume of momentum space, volume of the momentum space between momentum p and p plus dp is given by 4 pi p square dp divided by 8. So the volume of one quantum state, this is one quantum state, is given by pi h cut by L into whole cube. This you already studied in your statistical physics class. So the number of quantum state with momentum p and p plus dp is given by total volume divided by the volume of the one quantum state. So you will get 4 pi p square dp divided by 8 into pi h cut by L the whole cube. So when you divide this is h cut, h by 2 pi. So this pi get cancelled. 2 cube, that is 8, will come here. So this 8 and cancel. So the number of state having momentum p and p plus dp is given by 4 pi p square dp v divided by h cube. So this is the density of state for electrons. So when you consider the when you consider for the antineutrino or neutrino having momentum q, the number of state is given by dn is equal to 4 pi q square dqv divided by h cube. So that is for a neutrino. So we are going to write the wave function of electrons and neutrinos. Here we are assuming that electrons and neutrinos are free particles. So even though they are not completely free, we are approximate this particle to be free. So the free particle wave function is given by, and normalized wave function is given by phi e is equal to, the wave function of electron is 1 by square root of v e raised to I p dot r by h cut, where p is the momentum of the electron and phi nu is equal to 1 by square root of v e raised to I q dot r by h cut. So the wave function is wave function of electrons and neutrinos are this free wave function, free particle wave function. So we can and these values are very small, and we can approximate this into 1 plus p dot approximate into 1. So e raised to ip dot r by h cut is equal to 1 plus ip dot r by h cut, that is equal to 1. E raised to iq dot r by h cut, this can be approximately equal to 1. So we can write the d lambda as this, and the this can be so this can be written as d lambda is equal to 2 pi by h into g square mfi square 4 pi p square dp q square divided by h raised to 6 into dq by def. This is I will explain this. Okay, so this is the explanation. We know that we already discussed that lambda is equal to 2 pi by h cut vf phi square rho ef, and vp can be written as vfi, the final state can be written as if ox ii into dv. So this if state containing psi f star, this is the final state, and this is the wave function of the final nucleus, and final state containing electrons and neutrinos. So this psi f star, phi e star, phi mu star, ox psi I dv. So here when we apply the value of phi e star and phi mu star, we can write this equation as 2 pi by h cut. We can write the equation as 2 pi by h cut into, okay, so okay, we will substitute later. So this lambda is given by, this lambda can otherwise written as 2 pi by h cut vf phi square into dn by def, and we find out an expression for dn by dn as 4 pi square v square p square q square dq dp divided by h raised to 6. Okay, this is derived from, this equation is we can derive this equation from here. So here is, sorry, there is a change in the slide. Okay, so we get an expression, nothing to worry. So we will get an expression for dn into e, number of state, the density of state of electron having momentum between p and dp, p plus dp is equal to dn is equal to 4 pi p square dp into v divided by h cube. This will obtain from this expression. Okay, this expression. Okay, then for, in the case of a neutrino, when we apply the same theory for neutrino, the number of state of neutrino that is having energy between p and p plus dp is given by 4 pi q square dqv divided by h cube. So when we the total energy function dn, or sometimes it is called a d square, and or dn can be written as dne into dnu, multiple of these two number of states. So when we multiply this 2, we will get 4 pi square v square p square dp q square dq divided by h raised to 6. So here we are substituting dn. We are going to substitute for dn. Okay, then we know that we know the equation for the transition rate. In that equation we will substitute for dn. Actually we need as dn by def. So dn is substituting from here. Then we will substitute the wave function of this wave function, approximated wave function. This is known as allowed approximation. When we take the first term only, so when we take the first term of free particle waveform, this is called allowed approximation. This is an important term, allowed approximation. This is known as allowed approximation. If we take higher terms, we will discuss later. If we take higher terms, that is known as the forbidden state or forbidden approximation. It is actually forbidden approximations are not forbidden, and all allowed approximations are not allowed. Okay, that things will be discussed in the case of a case that we'll discuss when we discuss about the selection rules and all things. Okay. So we know that, so we will already learn these things. Okay, so this is this, so the wave function, the wave function is not, it is the decay probability or decay rate. Lambda is given by 2 pi by h cut into vfi the square, vfi square into dn by def. This is the number of state having energy, de. So energy between E and E plus D, or having energy D. So this dn is, we already know that dn is equal to 4 pi square v square p square q square dp dq divided by h raised to 6. So when we substitute for dn, and we already know that psi e is equal to 1 by square root of v, psi nu is equal to 1 by square root of v. So this so when we apply all these things to this equation, you will get lambda is equal to 2 pi by h cut square g square m fi square 4 pi square p square q square dp divided by h raised to 6 into dn by def. So this is the metric term which will represent the initial and final nuclear energies. So actually this is independent of the beta spectrum, and mainly the shape, it is mainly related to the nuclear interactions. We know that beta particles are not involved in strong interaction, so the contribution from this term is negligible, and main contribution is coming from these terms. So when we observe the shape of the electron spectrum, its contribution from Mi can be neglected. Okay, and all these terms are approximate into constant terms, are all the constant term is taken as C, and the energy distribution n of p dp is given by C p square q square dp. All these things, C containing all the constants, so n of p dp can be written as C p square q square into dp. If Q is the decay energy or Q factor of a reaction, then ignoring or negligible the nuclear recoiling energy, the so we know that N of P dP is equal to C P square Q square into dP. All these terms, other terms will come in this constant term. So we know that if Q is the decay energy, so what is Q? Q will be the decay energy, or the energy coming out from the nucleus. This will equal to the kinetic energy of the neutrino and the electron. So Q is equal to Qz, the kinetic energy of neutrino, plus Te. Te is the kinetic energy of the electron. So from that expression, we can write an expression for Q, momentum of the, what is Q? Momentum of the neutrino, that is Q minus Te divided by C. So when we consider the electron, we know that energy in the beta spectrums are in the order of 1 MeV and above 1.5, 1.2. So in like that. So the rest mass energy of the electron is 0.5 MeV. So we cannot neglect this energy because they are comparable. 0.5 MeV and 1 MeV are comparable. So we cannot we cannot ignore the rest mass energy of the electron. So we have to take the relativistic mass for the energy of the electron. So this is the relativistic expression for the energy of the electron. E is the energy of the electron. That square is equal to P square C square plus M square C raised to 4. So this energy is equal to kinetic energy plus rest mass energy the whole square. So that is Te plus M0 C c square the whole square. So from this expression, what is Te is equal to T is equal to square root of p square c square plus m square c raised to 4 minus m0 c square. So when we substitute for Te here, we will get an expression small q is equal to capital Q. This is the momentum and this is the energy of beta spectrum or beta decay or Q value of the reaction. Q minus square root of p square c square plus me square c raised to 4 plus me c square. So this, there is a negative sign, this will become positive divided by c. So this equation can be rewritten as n of p is equal to capital C divided by p square is there, p square is q is equal to q minus T by c. So q minus T the whole square by c. So our aim is to write this in terms of the energy of the in terms of energy and momentum of the electron. So we are converting the momentum of neutrino in terms of energy. So here c is a constant, c square can be taken, p square into q minus, here we are substituting for T, that is equal to square root of p square c square plus me square c raised to 4 plus me c square the whole square. This function vanishes at q is equal to 0, not p is equal to 0. The function vanishes at q is equal to 0. That is when q is equal to 0, the energy of the neutrino is equal to 0. So the total energy or the q value is equal to kinetic energy of the electron. So from this figure we can find out this. So this is n of p, the number of state having n of p is the density of state. So this is drawing with the momentum of the electron. So at this point, we know at this point q is equal to 0, or momentum of the electron have the maximum value p maximum. At that time neutrino energy is equal to 0. So the full energy is taken by the electron or beta particle. So this is the spectrum, this is the energy spectrum T graph. This is the maximum T where the neutrino energy is equal to 0. So this is the expected electron energy or momentum distribution. Actually we didn't get these expected values because of the approximation that is taken during these derivations. So when we take approximations, the actual graph is not exactly same as this graph. This is the expected graph, but actual situation is not this.